Converting negative integers to binary. F. Hello everyone and welcome back to another video. In this video, we're going to be talking about how to turn negative integers as binary numbers. So to start this off, we're going to look at just 4 bits of numbers and look at 1000 compared to 0111. When negative integers are involved, it is assumed to be if it's assumed to be a negative number, the leading bit is considered to be a negative indicator. Therefore, negative 8 is the most negative value when we have 4 bits, and let's examine that right now. Because the leading binary digit, the leading bit, is always going to be considered negative, and the following bits onwards are going to be positive. We will be adding positive numbers to this negative value, which is negative 8. And as we add positive values, as any of these 3 bits turn on, we're going to get less negative overall. So if we have negative 3, we know that it's a negative, so the leading bit's going to be turned 1. And then from negative 8, we need to figure out which bits I need to turn on to turn that into a negative 3. So negative 8, if I turn on the 4, that gives me negative 4. So I can't turn the 2 on because if I add the 4 and the 2, we get negative 2 back. So we're going to leave that off. And if we turn on the 2 to the exponent 0 bit on, we're going to be adding 1. Therefore, if I do negative 8 plus 4 plus 1, we get negative 8 plus 5. And we end up getting negative 3 returned. So what is the simplified instruction? Okay. So in this situation, we're going to be working with 8-bit integer numbers, and we're going to try to create any number from negative 128 to 127. And it's going to follow a 3-step process. Step 1, we're going to convert the number as if it was a positive number and in 8 bits. Then we're going to create the complement of that binary number that we generated in step 1. And then lastly, we're going to add a value of 1 to the complement. And 1 in 8-bit binary is its first 7 bits turned to 0 and the final bit being turned on. So for this exercise, we're going to be looking at negative 42 as a binary number. So our step 1 would be just treat it like a positive number and generate the binary number. And what we do is divide the number by 2, track its quotient and the remainder, and we stop when the quotient is 0. Okay. And then to make it into an 8-bit binary number, we're just going to add zeros to the front if it doesn't have 8 bits. So in this situation here, we're going to do 42 divided by 2. That gives us 21 with the remainder of 0. We haven't hit a quotient of 0 yet, so we can continue on with our division. So we do 21 divided by 2, 10 divided by 2, 5 divided by 2, 2 divided by 2, and 1 divided by 2. And we hit 0 there, and we have tracked our remainder as we have been doing our divisions. So from bottom to top, left to right, it would create 101010. So with 6 bits, we can represent 42 as a binary number. However, we wanted an 8 bits in the system, so we're going to go 0, 0, add the first, add the 0 so that we can have 8 bits in total to represent 42. Then in step 2, what we're going to do is create a complement. Complement of a binary number is its bits all turn to its opposite value. Therefore, if I have 001010, which was 42, the complement of 001010 is going to be 11010101, where we are reversing each individual bit to its opposite value. So 0 turns to 1, 0 turns to 1, 1 turns to 0, 0 turns to 1, 1 turns to 0, 0 turns to 1, 1 turns to 0, and 0 turns to 1. And we get 11010101. Perfect. Well, let's do a little aside. What is 11010101? We did a complement of 42. What would the complement of 42 be, assuming that our leading digit was negative? So we have 8 bits. That means our leading bit is negative 2 to the exponent 7. 2 to the exponent 7, all total to be negative. So we get negative 128, and that is currently turned on. The second bit is turned on, so we're going to be adding a positive 64. The fourth bit is turned on, so we're going to add 16. The The 6th bit is turned on, so we're going to add 4. And the very last bit is on, so we're going to add 1. So if we take negative 128 and add 64, 16, 4, and 1, we're going to get negative 43. And you'll notice that, hey, that is literally one value. You know, a plus 1 away from our desired value of negative 42. Therefore, in step 3, we're just going to add 1. So 1 in 8-bit binary is 0000000001, and we're going to add that to our complement 11010101 added by 00000001. Well, when we add binary numbers together, 0 plus 0 will give you 0. 1 plus 0 gives you 1, and 0 plus 1 gives you 1. However, if you add a 1 and a 1 together, it creates a 1. Oh, this creates an overflow. Well, that's because if you take 1 and 1, it creates binary of 2, where we can't represent 2 with a single bit. Therefore, we need to have an extra bit to create that information. Therefore, we need extra bits, and anytime this happens, we are creating something called an overflow. So in this situation here, if I added the 1 and the 1, the new 1 will be placed in the second line, and then the 1 plus 1 will give you a 0. And the new extra bit that required will be added in the second line here. And since they're all zeros, we're just going to carry down the one that we have generated and leave a 1. 1 plus 0 gives us 1. 0 plus 0 gives us 0. 1 plus 0 gives us 1. 0 plus 0 gives us 0. 1 plus 0 is 1. And 1 plus 0 is 1. So we really just maintain the rest of the unaffected bits as it is. And our second bit and our last bit have been affected to have 1, 0. And if we were to translate this back into a integer number, it would calculate to negative 42. So along that line, let's try another number, a bigger or more negative number, a negative 104. We're going to do the same thing, continuously divide by 2, so that we can generate the positive equivalent value, or the binary number positive 104. So we're on a 4, we're going to divide by 2, we get 52, remainder 0, and we continuously on until we hit that 0. So we go 52, 26, 13, 6, 3, 1, and then we have a remainder of 1. So therefore, we go backwards, and we want to have 8 bits. We're going to have 1101000, and to make it 8 bits, we're adding a 0 to the front so that we have 8 bits in total, because we have 1, 2, 3, 4, 5, 6, 7 remainder generated when we were continuously dividing by 2. Awesome. We're going to create a complement. That's when we reverse all the bits into its opposite value. So the complement of 01101000 becomes 10010111. Now, we have done step 1 and step 2. At this moment, we're going to take the value of our complement and add 1. So 10010111 is 104's complement. And we're going to be adding 1 to this value. And you'll see that a lot of overflow occurs, because 1 plus 1 will be a 0. And we're going to be bringing a new 1 to this placeholder, and there's a 1 here, so we're going to do another 1 plus 1. So there's 1 plus 1 that creates a 0, so we do 0 plus 0. There's that, and another 1 comes over on this line, and it will be 1 plus 1 that creates an overflow, so we have a 0 plus 0 remaining, and then there is no 1 here, so there's no potential overflow. We just end up adding 1 plus 0 to get this 1 right here. Therefore, a negative 104 is 10011000. So let's analyze it with just the 4 bits at the end. If I were to add 0111 plus 0001, that is equivalent to 7 plus 1, which is 8. Well, what is 8 in binary? 8 in binary is 10000. Because when you have 3 bits, the maximum number that you can generate is 7, is 4 plus 2 plus 1. That's the maximum number that we can generate with 3 bits. And if we add 1 to it, we create an overflow, where with the 3 digits we had here, we couldn't generate a number 1 greater than that. So everything turns off, and we just added an extra bit to express the value of 8. So that's where the overflow has occurred. And we'll do one final example here. We're going to turn negative 15 as a binary number. We're going to do the same thing, constantly divide by divide the number by 2, track its quotient and the remainder because we want the positive 15's binary number. 15 divided by 2 is 7, 7 divided by 2 is 3, 3 divided by 2 is 1, and 1 divided by 2 is 0. And all of our remainders are 1 because 15 as a binary digit is 0, 0, 0, 0, 1, 1, 1, 1, 1. So that is 15 as an 8-bit number. With that, we're going to generate a complement. So if we generate a complement of 0, 0, 0, 0, 1, 1, 1, 1, we get 1, 1, 1, 1, 0, 0, 0, 0. Okay, so we have kind of flipped that. And then we're going to add 1. This is very simple. There is no overflows occurring. 0 plus 1 gives us 1, and everything else is all 0 plus zeros or 1 plus zeros. So we just go straight down the middle, straight down the line, and negative 15 will be expressed in an 8-bit system as 1 plus 1 plus 1. 1, 1, 1, 1, 0, 0, 0, 1. Now, you might be thinking, well, how can I check if 1, 1, 1, 1, 0, 0, 0, 1 is actually negative 15? Well, that's when you can use this table. When you have 8 bits and you understand that the leading bit is negative of 2 to the exponent 7, you'll have negative 128. And if it's a negative value, this will always be turned on. And then you add the 8-bit binary numbers you have into this bit called a bit row here, and you get the total integer sum. So let's try that. It's 11110001 negative 15. So leading bit is 1, so we know we have a negative value. 64 is turned on, 32 is turned on, and 16 is turned on, so we're going to add all those values. 8, 4, 2-bit are all turned off, so we're going to be adding nothing, and then we're going to add in a value of 1. And if we total all that up as a sum, we get negative 15. All right. So that was a nice little quick video in terms of how we can convert negative integers to binary numbers, and this entire process is called using the 2 complements method. And as always, thank you for watching and stay classy.